Now let us call for the next presenter. Next presenter is from MB Power, Madhya Pradesh, Hindustan Power Projects Private Limited, Anuppur, Madhya Pradesh. Forecasting APC in coal-based thermal power station through multi-variate regression analysis. It will be something interesting project, right?
Good afternoon, ladies and gentlemen. My name is Arun Agarwal, and I look after planning and efficiency department in my company, Hindustan Power, as sir has told. I'd like to thank SOPEP for this opportunity to give us a present over here in the paper, forecasting of APC in coal-based power plant through multivariate analysis. Since a disclaimer, this is my first presentation in such a big forum. I would be giving you, please, what to say, please bear with me for my presentation. Now, coming to the forecasting of auxiliary power consumption, there is a great saying by Jack Paints that what gets measured gets corrected. Now, understanding the factors that affects auxiliary power consumption is in a coal-based power plant, and determine whether the power consumption consumed by the power plant has been optimal or not. It is very difficult to measure. Unlike other performance parameters such as heat rate, which technically use coal-based power plant measure difference between actual and design, but which is OEM provides us. But however, in OEMs does not provide any definite guidelines for or benchmarking for auxiliary power consumption. Now coming to introduction of the coal-based power plant, as Mr. Chattopadhyay sir has already explained all technicalities with a beautiful diagram of thermal power plant, and we are from thermal power plant, so we are used to that technicalities. So I will skip this part. And now coming to the auxiliary power consumption, as Chattopadhyay sir has already explained this also regarding auxiliary power consumption. So I will just broadly tell you that auxiliary power consumption is broadly defined as the in-house auxiliary power, which largely depends upon the plant load factor of an unit. Now, as you can see that in a typical thermal power station, the auxiliary power consumption is around 8.34% to 9%. And as the significance of APC reduction, with 1% of APC reduction, we can improve our net heat rate by 10%, which is a huge cost. It will reduce our coal consumption as well as the carbon footprint of our planet. So it is so much important to us. And of course, the benefits of organization is also counted in that. The significant drives that consumes auxiliary power are basically in a power plant is boiler pit pump, condensate extractor pump, post draft fans, ID fan, FD fan, ID fan, FD fan, PA fan, then boiler circulation pump, mills, cooling water pump, coal handling plant, ash handling plant. These are some, I will not go to the details because these are we will measure in next slides. Now coming to the methodology, means how we are forecasting our APC. That at a designed PLF or a scenario where the PLF is suppose at a say 60%, 80%, and the ambient temperature is very different. So how can we forecast APC so that it shows us that how much expected APC should be there and how we are running at these conditions. So what we do is the power consumption of all major drives are on a particular day in a 24-hour is manually recorded because we don't have any EMS system in our unit. So at 00 hours. Now based on the historical power consumption of each drive of 2 years and running hours of each running drives, regression is done and generated a coefficient and a constant. Expected auxiliary power consumption of a unit is measured, and all other expected auxiliary power consumption we get it, and all major drives is compared with actual consumption with identified with improvement areas. Now coming to the regression analysis. Regression analysis is a statistical method to determine the dependence of a various independent variables with a dependent variable Over here, we can see that our dependent variable is auxiliary power consumption, and we are going to estimate that how our auxiliary power consumption has been with the present condition. Now, we have to gather some information for that. That is the independent variables. There are two variables we have to again we have to understand. That is, one is dependent, one is independent. So dependent is that in which independent variables are connected to it. If the independent variables gets changes, the dependent variable, that is auxiliary power consumption, will also change. So the independent variables which are in controlling APC are plant load factor, specific coal consumption, total moisture, primary air pressure, oxygen at APH inlet, ambient temperature, relative humidity, then transport air compressor running hour, instrument air compressor running hour, barrage running hour, AVGF running hour, coal mills, total coal mills running hour, ash water pump house running hour, DM plant running hour, hydrant pump running hour, and jockey pump running hour. Now coming to the previous year data, means I have already told you that we taken a set of data for around 2 years, and we compare that with our regression model. So what we do is we take all the data, as you can see over here. These are the data for, I've given you only 5 to 6 days, but it has been always recorded for at least 2 years. This data has been collected. Over there we do a regression analysis. With this, the APC will be your dependent variable, and other these parameters are independent variables, which will contribute to your APC. Now what we do is we do a regression model for this. And when we do a regression, you can see that our R square is around 0.90, which is quite good. Means it gives us an accuracy of 90% over here. So with this, these are the coefficient of all the independent variables which will factors to our increasing or decreasing of APC. As we can say that obviously PLF, with increase of PLF, it is a negative coefficient. Means with the increase of PLF, your APC will reduce. And the biggest contributor over here is SCC, that is specific coal consumption. That amount of coal is required to burn to increase the load. So over here the maximum is 1.19%. And other factors are also contributing. Just the pH pressure, oxygen, all this has been given with plus and minus signs. Plus means that it is increasing the APC, and minus sign indicates it decreases the APC. Now let us understand this with an example so that we can understand very clearly how it is affecting and how we are calculating our APC regression model. So for an independent variable, these are the, I already explained, these are the 14 independent variables which we are taking for a particular day. Means in a particular day we are having that our PLF is 73%, SCC is 68, pH pressure is 7.98, then O2 is 3.5%, ambient temperature is 18.9, and other running hours which has been running for all the parts. Now coming to the mathematical illustration, what we do is, once this, as I already told you, these are the coefficient which we are getting for independent variables, right? So when we do a mathematical illustration, what we do is, the running hour which we are getting, which is the mathematical coefficient of it, we multiply with that and sum it up with all these things along with a constant. So what we do, this is the mathematical expression which I want to, I've shown you over here. The same thing is written in a manual setup. But we get an outcome over here. You will be surprised that the outcome as a regression model is that expected was 5.93 APC. But we are actually run at 5.79%. So there was a deviation of positive. It means it is a good that expected. We were expecting at 5.93% of an APC, but we have actually done better with 5.79% of an APC. We have a deviation of minus 2.75. That is good. Similarly, we have done all these things with, this was an APC for ID fan, FD fan, all the equipment, major equipment level based we have gone through. and we have determined that equipment level, how our equipment has performed, and which is contributing to APC. Now, but we can see that for IDFAM, it was expected that it has for a day it should have consumed a 61 megawatt, but has it actually consumed 69 megawatt. There has been a deviation of 14% in that. This shows all the equipment by percentage how we have done, how we are doing as an equipment level also. Because for APC, if you do not control in equipment level, your final outcome of APC will not be good. So what we see is, for example, for over here you can see that it has been shot up by 289%. Okay, this is a very big outlier which you can see. But the catch over here is that our regression model has already up 2 years, and since it is running in a VFD, our consumption has reduced from 75 megawatt to 19 megawatt due to VFD. So the regression model has already anticipated that in this kind of actual condition, you should have consumed around 19 megawatt, but we are expecting we are consuming 79% at that kind of 73% PLF. So it's already showing that the VFD was out, and this regression model can show that it has going shooting up very drastically. These are some AHP and all this equipment price level we can see over here. Now the results. Now to make this PPT or the model a viable one, because we need a set of parameters over here. Parameters which we take is of 479, because out of 2 years data there are a lot of unit shutdowns and outliers are there, because that we remove all the the plant which has run around 30% or 40%, we have removed from 40 to 100% PLF. We have taken all the data from 40% to 100%, and we have made a regression model. And with to make it very viable and very dynamic, what we have done is that we always do, we continuously change the parameters with the old ones. Means every 2 years data we will take, and with today's suppose today we have taken a set of reading, we will replace that with an old one, so that all the parameters of it contributes the present 2 years format, and it gives us the current condition of the plant with how much regression is required. Since we use over here the independent variable using is our MS Excel lineage function. It is a very good tool in MS to use a lineage function. It keeps on changing the regression model of this this coefficient. It gets changes. So we get a new coefficient, and hence a new expected data starts coming for that. These are some results about the APC for unit 1. I have shown you for unit 1, unit 2 also we have done, and station we also get it. So actually we can see that we have done good in APC on unit 1, unit 2. And when we break up to the BTG and BOP, this is part of BOP. It's not showing over here. So we can see that in unit 1, unit 2 BTG part we have done good, but coming to unit 1 BOP area, we are losing around 7.2%, which we could have done better. These are some more results of equipment price. Suppose TDVFP, CEP, CCCW, and the red marking shows there is a deviation which could have improved. And similarly, the ESP, LT, PMCC, I think these words will be more important to power plant person. You can understand how important this is. Then these are the present set of data for the day, which I have already told you. These are some more results of CHP, AHP, all this actual what we have consumed and what is the expected. And the red line draws us how much more it has consumed. Now coming to the conclusion part. Now coming to the conclusion part, we can say that our unit of station drive specific agricultural consumption may be projected by using multi-variate linear regression analysis outlines above, means before slides, and pave the road for our future continuous improvement. Similarly, it also gives us an overview of our drive performance, and it clarifies that if the drive is using more energy than necessary or for particular load and operating at an operating environment, suggesting that the drive is either inefficient or it is the inefficient of the operator, and such corrective actions can be taken. Now, limitations to this regression analysis is that our biggest drawback for now is that we record this thing in manually. All the energy meter correction and the meter recording is done in manually, which are based on data collection, which increases our cumulative error due to delay in energy meter recording and not recording at the same order as in past. It might be having typical mistakes also and extra. And the model inaccuracy is now restricted to 90% because we have taken a very small data of 2 years. But we are sure that the accuracy is anticipated to rise with the inclusion of more historical data and the state of future. Thank you, sir. Thank you.
Question, please.
Yeah.
Please pass it there if you don't mind.
Since the model is developed on the basis of regression,
Yes.
so the first thing is we are making the model on the basis of predicted value. So for predicted value, you are using a historical data.
Yes.
But when I predict the value of the equipment today based on its current say 2 years back, there is some deterioration that takes place. So how are you going to adjust? Because आज मैं देखूंगा करंट हो सकता है कि 2-3 आज ज़्यादा चलेगा, 1 महीने पहले या 2 महीने पहले वो मतलब करंट दूसरा रहता है, क्योंकि हर इक्विपमेंट डिटोरेट करता रहता है.
Exactly.
So how do you take care of that in this model?
That,
and one more thing I will just put up
yeah,
that on
please.
you have put predicted value and actual value and made a deviation. Okay. Say a coal mill current में deviation आया आपको. Historical value and present value you have got a deviation. But that deviation is always not due to the maybe आपने जो parameters consider किया उसकी वजह से. There are many more parameters which affect the performance of the mill. Suppose say my mill current has increased today, but it is definitely not because of the loading or some deterioration. There might be other factor also. Say some coal comes which is having more moisture content, or coal which is not of good quality, sent by the same vendor or something. Again, that factor affects, and I will not come to a conclusion that okay, my equipment is not performing well because the current is more, because there are some other factors which overall contribute to that regression. So how are you taking care of it? That's my question.
Yeah. First of all, let me answer the first question. Is that how we will compensate with the new environment which are continuously generating?
Yeah, equipment.
Yes, equipment level, right? So I have already explained that कि हम लोग जब भी can I speak in Hindi also? It is okay. So हम लोग यहाँ पर क्या करते हैं? हम जो डाटास लेते हैं, हम लोग आपको ये जो डाटास है इसको हम कंटिन्यूसली चेंज करते रहते हैं. मीन्स आज जो डाटा आया है, हम जो ओल्डेस्ट पार्ट रहेगा, जैसे 2 साल पहले का जो भी डाटा रहेगा, उसको हम लोग रिप्लेस कर देते हैं. सो दैट जो हमको हमें जो भी बैकअप्स मिलता है, दैट इज द कम्प्लीटली न्यू एंड डिफाइंड डाटास. सो वो चीज़ हमें व्हाट इट डज इज दैट इट चेंजेस ऑल द सिनेरियोज. द कोफिशिएंट ऑफ दिस मॉडल ऑलवेज चेंजेस.
ये जितने भी कोफिशिएंट्स आपको दिखते हैं, सॉरी,
These are the जो भी आपको कोफिशिएंट्स दिख रहे हैं यहाँ पर, ये सारे चेंजेस होते रहते हैं एवरी डे, क्योंकि इससे चेंजेस से आपको एक प्रेडिक्शन हमेशा मिलते रहेगा कि वो नए पुराने जो डाटा वो हट जा रहे हैं, नए डाटा आ रहे हैं, उससे हमको एक नया कोफिशिएंट मिलता है. तो इट गिव्स यू फर्स्ट आंसर दैट प्रेजेंट डे कंडीशन में क्या हो सकता है. नाउ यू आर राइट दैट कि समटाइम्स ड्यू टू कोल मॉइस्चर and all these things, we have taken that in our previous year. Total TM consumption, total moisture, GCV, we have taken that. When I have done a regression analysis for that also, for a particular mill, because mill requires GCV, your total moisture, ash content, all these things are required for understanding the mill condition. But when we found that the coefficient was significantly less, so that does not give us any more input to that for what to say expected. I have already tested that. I have taken all the consideration for that, but it was also surprising for us also that because of that our expected has not changed much. So and still yes, there may be chances of 1% or 2% because of this because its accuracy is 90% right now. So.
I think accuracy will increase much more further if we consider more
exactly
variables.
More variables.
We are doing the same thing. We are using more variables to get to a predicted value. So when you, but you need more Oscar value, better Oscar value. So we have to see which are the values which are giving the maximum outlier. We have to remove them.
Yeah.
The values which are suiting your regression that we can use, and we can further improve the.
Actually, the thing is that before that, if you see in this presentation, these running hours we have not taken before. So once it was our R-square value was around 85% before. Sorry, sir. So, but now it has gone to 90%.
अच्छा, he has one question. Before that, मेरे तो सिर के ऊपर से सब गया. I do not know these people have understood really. You give it to him. It is the last question, so be as brief as possible.
Actually, my question was that what is the accuracy level? But you have said that it is 90%, I think.
Yes, yes.
And the second one is that how much past data you are comparing with?
Now presently we are taking around 2 years data. It has been data over here. Now in this regression model we have taken 479 data. After removing all the shutdowns, less than 40% PLF, all these things we have removed.
Okay, let us stop it here. Hello,
Okay,
let us stop it here. मेरा सिर के ऊपर से गया, but you people have understood means you are definitely greater than me, much greater than me. Thank you very much. So I will tell you one correction here, Mr. Chattopadhyay. Actually, your paper was, I think it is technical paper number 11, but you have spoken in place of number 9. So we are correcting it. So let us go to the paper number 9, harnessing employees' creativity for enhancing safety and business performance. In future, don't keep the same title because it is really confusing and it is going to happen. Such type of confusion is going to happen if all the titles remain same from the same company, right? So would you like to speak? Present? Now, if there is time, if you want, we can give you.
Yes, sir.
You have already spoken, sir. ये भी आपका ही है, हाँ? ओके, आ जाइए सर, नो प्रॉब्लम.